Hi everyone. So in this video, we're going to be talking about inverse trigonometric functions. So this is a topic that we're going to be spending several videos on, and this is really going to be our first introduction. So inverse functions in general is a topic that you should have studied in your 141 or pre-calculus 1 class. We're going to be spending a little bit of time reviewing inverse functions in general at the beginning of this video, and I'll also link my videos from 141 about inverse functions in general, because I think if you're kind of rusty on what a function and its inverse, what that really means, you might find it useful to look back at those videos. But yeah, so we're basically just going to apply the ideas of inverse functions in general. We're going to apply those to trigonometric functions. And one thing, I'll get to this later on in the video in a little bit more detail, but inverse trig functions, by the way, that is completely different than the reciprocal trig functions, right? Reciprocal trig functions are their own thing. That's like cosecant, secant, cotangent. Inverse trig functions means something completely different. It's really the word inverse is being used in the same way that in 141 it's used when you talk about inverse functions. Okay, so I want to do a quick review about not everything about inverse functions, but some things that I think will kind of help you understand better how inverse trig functions work. So some basic facts about inverse functions that I think will be helpful. Okay, so when I describe, in 141, like what is the deal with a function and its inverse function, one word that I tend to use a lot is this word reverse or reversal. So a function and its inverse, in a lot of different ways, they're kind of opposites, or you'll see that certain aspects of them kind of are swapped compared to each other. And so I want to write down a few different ways that you can kind of see them as being these reverses of each other. So the first thing I would say is that if you have a function and its inverse, they perform the reverse action of each other. And what do I mean when I say action? Well, this might not be how you typically think about a function, but anytime you have a function, so let's say, for example, f of x is equal to x cubed, that function is performing an action on the input, right? So for the example of f of x is equal to x cubed, what is the action that this function does? Well, it takes your input and it cubes it. And so what would be the inverse function? What would be the function that takes that action and reverses it? So in other words, what is kind of the opposite of cubing something? Well, that would be taking the cube root. So in other words, the inverse function of f of x is equal to x cubed is the cube root of x. They would undo each other, right? Cubing and taking the cube root would undo each other. So another thing that's important to understand about functions and their inverses is that their inputs and outputs they swap roles. And so I'm going to continue on this page using these two functions, f of x is equal to x cubed and the inverse function is equal to cube root of x. I'm going to use those as my examples throughout. So for example, if you take the function f of x is equal to x cubed and you have an input of 2, what is your output going to be? Well, it's going to be 2 cubed and you get an answer of 8. And so the input is 2 and the output is 8. So on the other hand, if you look at the inverse function, if you now plug that number 8 in as your input, so remember, originally, this number 2 was your input, and this number 8 was your output. So what I'm saying here is that if you now take the inverse function and you plug in the output from the original function, but now you treat it as your input, let's see what happens. Well, you take the cube root of that number, so in this case, that would mean taking the cube root of 8, and your answer is 2. And so what happened is that the inputs and outputs swapped places, right? The number that was originally the input in the original function is now the output in its inverse function and vice versa. So that is always going to be the case for any function and its inverse. Another thing, and this we're not really going to get into so much in this video, but it'll come up in the next video, is the relationship between an inverse function and its graph. So if you have a function and its inverse, those two functions, if you look at their graphs are going to be reflections of each other. And specifically, they're reflected over the line y is equal to x, or I like to use the word about the line y is equal to x. And so the line y is equal to x, that would be a diagonal line with a slope of 1, right, like this. And so if you look at these two graphs, and I might have gotten the colors no good. I matched the colors up the way I wanted. So this is the graph of x cubed. And this here would be the graph of its inverse function, the cube root of x. And notice that they kind of have this symmetry, right? If you took the original graph, the x cubed graph, and you reflected it over that diagonal dotted line that I just drew, it would look like this blue graph. And another way of thinking about the relationship between the graphs is that basically the x and y coordinates are going to switch places. So let me write that down and then I'll show you an example. So their x and y coordinates basically swap with each other. So for example, if we look at the graph of x cubed, way up here we have the point 2, 8. And then if we look at the inverse function is going to contain the point 8, 2. So the x and y coordinates are switching places, and that's really equivalent actually to reflecting over the line y is equal to x. And then the last thing, and this is actually the functions I chose, x cubed and cube root of x, are not a great example for this, but it is true in general that the domains and ranges are going to swap with each other. So the reason that, and maybe what do I mean by that? I mean that the domain of your original function will become the range of its inverse, and then the range of the original function will be the domain of the inverse. So they have swapped domains and ranges. The reason I'm saying that these functions are not a great example is because for f of x is equal to x cubed, its domain and range are actually both all real numbers. And so if you switch those, it's still domain and range of all real numbers. So basically both the function and its inverse in this case have a domain and range of all real numbers. But if you had a function whose domain was not all real numbers and whose range was not all real numbers, you would then kind of see in the inverse function those two domain and range getting switched. Okay, before we get into inverse trig, I want to do one more example, and this example might seem a little silly and unrelated to what we're doing. But the reason I'm going over it is I really want to dig into this idea of the roles of the inputs and outputs swapping places, because that's going to be really, really important when we get into looking at trig functions and inverse trig functions. So let's say that you go to a carnival, and at this carnival it costs $5 to enter, just to get in through the gates, but then you additionally have to pay $2 for each ride. So I want to write down a function f of x that would tell us the cost of going to the carnival and going on x rides. So maybe pause the video and try to come up with that yourself. So how much would it cost to attend the carnival and go on x rides? Well, it would end up being 2x plus 5, right? Because basically, 2 times x, that's going to give you an extra $2 for every ride you go on. And then this plus 5, that's just always there because it costs $5 to enter. So this would be the function that would give you the cost for going on x rides. So what do the input and the output represent in this example? Well, the input represents the number of rides. Right? For example, if you go on 3 rides, you would plug in x is equal to 3. And then what does the output represent? Well, the output represents the total cost. Maybe I'll say total cost. And maybe just to do one quick example. So for example, let's say you wanted to evaluate f of 3. So f of 3 would be equal to 2 times 3 plus 5. And so that would give us 6 plus 5, so that would be 11. And so what does that number 11 represent? Well, that represents the number of dollars, right? Or the cost, maybe I'll say it this way. Actually, I'm going to just write dollars. So it represents the cost, but specifically it's referring to dollars, right? $11, whereas this 3, that's referring to the number of rides. So input is rides, output is dollars. Okay, so what about the inverse function? Well, I don't want to, and by the way, this is not something that you're going to have to do for inverse trig functions. I don't want to go through the whole process of, how do you find the inverse function of a function like that? That's something that you should have learned in 141, and if you don't remember it, you can always go back and watch the videos that I'm putting in the description for this video, the 141 videos. But basically, the inverse of this function would be x minus 5 over 2. Again, if you don't remember how to do that, you can go watch the 141 videos for a refresher on that. Okay, so how would this inverse function work? That's really the point of this example, is not so much like coming up with the inverse function. I want to understand what the inverse function would tell you. So what kind of a number, what would the meaning be of the input, and what would the meaning be of the output for this inverse function? Well, remember, with a function and its inverse, the inputs and outputs are going to swap roles. And so in this case, the input would be the total cost, whereas the output would be the number of rides. And so just to do an example, and we'll do the example that corresponds with this one, let's say you plugged in 11 as your input. So if you plugged in 11 as your input, you would get 11 minus 5 divided by 2. And so that would give you 6 minus 5, 11 minus 5, which is 6, over 2, which is 3. And so notice that how this function works is that this time you're plugging in the number of dollars that you spent, or maybe that you have to spend, and out comes the number of rides. So basically, the original function is like, if you know how many rides you want to go on, it will tell you how much it costs. And then the inverse function is kind of working backwards. It's like, if you know how much you have to spend, or you know how much you ended up spending, it helps you work backwards to figure out how many rides you went on, or how many rides you could go on for that amount of money. So that's really what I mean when I talk about a function and its inverse, the inputs and outputs having these kind of opposite roles to each other and really switching with each other. Okay, so I want to get now into inverse trig functions. So basically, we just talked about inverse functions in general. And so everything that we talked about so far in this video is going to be applicable to trigonometric functions, right? Trigonometric functions are a function just like any other function, right? We've studied their graphs, we've done transformations of their graphs. Now we're ready to work on their inverse functions. So by the way, in this video, we're going to be focusing on inverse cosine and inverse sine. We're going to do inverse cosine first. And then in our next video, we're going to introduce inverse tangent. We're not going to be looking at inverse functions for the reciprocal trig functions, just because they're kind of unnecessary. Like really the reciprocal trig functions can always be rewritten in terms of the original ones. So there just really isn't like much of a use for coming up with their inverses or anything like that. Okay, so this is going to take a little bit of kind of build up. I want you to hang in there. Some of what I'm writing might seem a little vague or wishy-washy. Eventually, we'll get to a very concrete definition, but I want to build it up with some intuition for kind of why things work the way they do. Okay, so first thing we need to say is basically introduce some notation. So the inverse function of f of x is equal to cosine of x. And actually, before I go forward, there's one thing I need to mention, which is you might notice so far in this class, we've been using t as our input variable, right? We've always been like f of t is equal to cosine of t, sine of t, whatever. it really doesn't matter what variable you use. We're going to switch to x because we're going to be using the same variable for the function as well as its inverse. And because t kind of has this significance, we kind of think of it as representing an angle, right? We think of it maybe as standing for theta. In order to kind of get rid of that significance to the variable, we're just going to use x because x is a very kind of generic variable. That being said, I really don't want you to confuse this x with like the x of the x coordinate on the unit circle. It has nothing to do with that. We're just using x because x is kind of a typical variable to use in a function, right? You could say f of t is equal to cosine of t. You could say f of theta is equal to cosine of theta. You can use whatever letter you want. We're just using x. Okay, so what is the inverse function of cosine? Well, there's a special name for it, and it's written like this. So it's written as f inverse of x, if we wanted to use function notation, and then the actual function is written like this, inverse cosine of x. So basically, you know, with a function like x cubed, the cube root is kind of the natural inverse of it. We didn't need to like come up with a whole new function. It kind of naturally had that reversal. For the trig functions, we have to kind of create a new function to be their inverse function. It's kind of like, if you remember with exponential functions and logarithms, those are inverses of each other. And those are not, you know, logarithms are kind of these functions that you had to put some work into understanding. And it's really similar with inverse trig functions. They're not just like, oh, just take the cube root. It's really its own function that you have to kind of build up some understanding for, the same way you did with logarithms. Okay, so how do you read this out loud? This cosine with the little -1, you would read that out loud as inverse cosine of x. So cosine with the little -1 literally just means inverse cosine. And so that actually brings me to something important that is a misunderstanding that I've seen students have, and it's a very, I understand why students would have this misunderstanding, but it's really important that you don't have it. So basically, when we look at something that looks like this, where it's, you know, cosine or sine raised to a power, usually we kind of have a meaning for that. That just means raising cosine to that power. So let me write down what I'm trying to say here. So usually, if you put an exponent between, you know, cosine and its input, the way that we have here, right? Here we have this little -1 nested between cosine and its input. You know, usually what this means is it's an exponent, right? So usually putting an exponent between cosine and its input represents raising cosine to a power. Right, so an example of that would be something like if you write down cosine squared of x, you know, that's just kind of a shorthand, that's special notation for meaning you're taking cosine of x and you're squaring it. And then similarly, if you take, you know, cosine and you put a little 3, well, that would just mean that you're taking cosine of x and cubing it. So usually that's what it means. However, that is not the case here. So that is not the case here. So that little -1 does not mean that we're raising cosine to the -1 power. So if you see something like this, cosine with this little -1 of x, that does not mean the same thing as taking cosine of x and raising it to the -1 power. I know that might seem like a confusing statement. I'll explain what it does mean in a second. But if you had this, so if you had cosine of x raised to the -1, what's another way of writing that? Like, what does it mean to raise something to the -1 power? Well, a number raised to the -1 power would just be 1 over that number. So cosine to the -1 would mean 1 over cosine. And we already have a name for that, right? That's secant. So that is not the same thing. Inverse cosine of x is absolutely not the same thing as secant. All this -1 means is inverse. It's literally a symbol that means inverse. So the negative 1, maybe let me make this capital, kind of separate it out. So the little negative 1 you see is just a symbol. And it's a symbol specifically meaning inverse. So hopefully this doesn't make things feel more confusing, but all I'm saying here is basically usually when we see a little number up here, it means you're raising cosine to a power. In this case, when it's a negative 1, it does not mean that. It just means inverse. And inverse does not mean 1 over. Inverse means the reversal, like all the things we talked about on the last page, right? Inputs and outputs, swap places, all of that good stuff. That's what I mean by inverse. I do not mean 1 over. I do not mean reciprocal. That is a completely different concept. And so because of that confusion, there is a different way of writing down inverse cosine. We're going to write it like this because that's what your textbook does, and it's a little bit more common. But another notation that you'll sometimes see, so I just want you to be kind of aware of it, is like this, arc cosine. It looks like it's something completely different, but it actually means the exact same thing. So inverse cosine and arc cosine are just two different ways of saying the exact same thing. We're going to use inverse cosine as our notation, but you probably will see arc cosine come up at some point, maybe in your calculus class. It is also a very common notation. Okay, so now that we got all of this, what not to do out of the way, let's talk about what inverse trig actually does mean. So I want to start with an example, and we'll start with this example, and this example is going to be a little bit of an oversimplification, but once we get through this example, we'll use it to get into a more kind of concrete definition of what inverse trig is. Okay, so let's say that we have our original function f of x is equal to cosine of x. And let's say we want to evaluate f of something, f of an angle, right? So f of, let's say, 2 pi over 3. Okay, so how would we go about finding f of 2 pi over 3? Well, we would go to an angle of 2 pi over 3, which would be like this, right? 2 times 60. We would write down the coordinates of this point. We would say, okay, it's negative 1/2 as the x coordinate, root 3 over 2 as the y coordinate. Cosine, and actually let me maybe scooch this over because I think I need a little bit more space here. So what is cosine? Cosine is the x coordinate, right? So here I'm going to write cosine of 2 pi over 3, right? Because that's what we're doing here. And then cosine of 2 pi over 3, well, using the information we have here, that would equal negative 1/2, right? So nothing new so far, right? This is just trigonometry. But the thing that I want to really emphasize here is, what is the input and the output? Well, the input is an angle, right? For a regular trig function, the input is an angle. And then what is the output? Well, the output is a number. And, I hesitate to use the word number because it's very vague, because angles are also numbers, right? Like 2 pi over 3 is also a number, but it's a number that has a little more meaning to it, right? It's a number that really represents an angle. Whereas the output is a number, and specifically maybe we can say it's a number between -1 and 1, right? Because with trigonometry, you're never going to get for sine or cosine an output that is bigger than 1 or less than -1. So the output will always be a number between -1 and 1. Okay, so let's think about how the inverse function should work based on everything that we talked about on the previous page, right? We did all this kind of build up about how inverse functions work in general. So if we wanted to evaluate, f inverse of something, what kind of thing should we be plugging in? What kind of a number? Maybe if we wanted to take this specific example and kind of reverse it the same way we did here, right? Here we had, okay, here's our original function, f of 3 is equal to 11. Then we did the inverse function and we found that f of 11 is equal to 3. What would be like the similar kind of situation here? Well, for the original function, we had that f of 2 pi over 3 was equal to -1/2. And so the way that the inverse function is going to work is we would say f inverse of -1/2. So in other words, inverse cosine of -1/2 So what should that be equal to based on kind of our general understanding of inverse functions? Well, it should be equal to the input from the original function, right? A function and its inverse should reverse the roles of inputs and outputs. So if the input for the original function was 2 pi over 3, well, that should be the output for the inverse function. And so notice here that now the input is a number. Specifically, it was a number between -1 and 1, between -1 and 1. And now the output is an angle. So if there's nothing else that you get out of this entire video, and we are definitely going to get into a lot more detail in this video, but if you get lost in the details, if there's only one thing that you can remember about inverse trig functions, I want you to remember that the input is a number and the output is an angle, right? For regular trig functions, input's an angle, output's a number. For inverse trig functions, that switches. Okay, so now I want to get into kind of the more like official definition of what inverse cosine of x is, right? Because this was just kind of an example. And we'll see that there's something that I didn't really say on this specific example that we're going to need to kind of get a little bit more technical about. And then we'll kind of come back to this example and see how things kind of change. One other thing I want to mention is that for most of this video, we're not actually going to be using function notation like this. We're not going to be writing down, and I actually forgot to do it here. We're not going to be so much writing down like f inverse of x. We're just really going to be saying, inverse cosine of something in the same way that, usually when we're dealing with sine and cosine, we're not writing, f of 2 pi over 3. We're just saying cosine of 2 pi over 3. Okay, so basically, I'm going to write down kind of a first definition here. So inverse cosine of a number x is equal to an angle theta if cosine of the angle theta is equal to x. So this is basically what we wrote down in the example above, right? Or what we saw happen in the example above. So the inverse function, the input and the output kind of switched compared to the original function. And that's really all this is saying here. But there's kind of another way that I like to think about this, which is I like to think about doing the inverse trig function as kind of asking a question. So I'm going to kind of phrase it that way. So in other words, you can think of inverse cosine. If someone asks you, hey, what is inverse cosine of, -1/2, right? That's what we did up here. Inverse cosine of -1/2. You can think of that as kind of asking you a question. It's asking you to find something. It's asking you to work backwards. Specifically, it's asking you to find an angle theta. So work backwards, find that angle theta, and I'm going to leave a little space here because we'll see there's a little bit more we need to write down, but we'll come back to that in a moment, such that cosine of theta is equal to x. So second thing I wrote down is really not too different from the first thing. I just wanted to kind of make it a little bit less symbol heavy and more like a sentence, right? So if you're taking inverse cosine of a number, you're looking for an angle such that cosine of that angle gives you the number that was in the original parentheses. Okay, so I keep alluding to these extra details. So what are these extra details I'm talking about? Well, going by this definition, if we look back at the example we did above, so when we found f inverse of -1/2, so inverse cosine of -1/2. So up above, we decided that that was equal to 2 pi over 3, right? Because that was our angle that we went to. So here's our angle of 2 pi over 3. And we found that cosine of that angle was equal to -1/2. And I'm actually going to take this and copy it and paste it down below because I want to kind of refer to it. So let's see, copy. But why couldn't it be a different angle? So, looking at like the definition we had above, right, we said that if you have cosine of an angle is equal to a number, then inverse cosine of that number is equal to the angle. So my point is that there's other angles that also have cosine equal to -1/2, right? So just to give another example, well, what about this angle here? Right, this angle here also has an x-coordinate of -1/2, and then the y-coordinate would be -√3/2. And so what is this angle? Well, you could measure it as a negative angle, you could measure it as a positive angle. Maybe I'll just measure it this way. So what would that be? Well, this is 2π/3, 3π/3, this would be 4π/3. And so I don't know, why wouldn't 4π/3 also work? Right? It's like if we're just looking for an angle such that cosine of the angle is -1/2, it seems like 4π/3 should work. And then we could even come up with more, right? We could measure it this way. We could say, well, okay, what about -π/3? That seems like that should also be an answer. And even further than that, we could actually go around the unit circle more than one time. We could go to this angle of 2π/3, we could go around and then again, and that would give us an angle of, I think, 8π/3. I know this picture is getting a little crazy, but 8π/3 would be like coterminal with 2π/3. So are all of these correct? Like, is inverse cosine of -1/2 equal to all of these things? And the answer is no. And really the reason for that is that inverse cosine is supposed to be a function. And if you think about the way that functions work, you're supposed to plug in one number and get one number out, right? It's not supposed to be like f of 1 is equal to 3 or -7 or 10 or 12. It's supposed to be like f of 1 is equal to 3, right? Function, one input, one output. And so we need to basically make an adjustment to our definition so that we don't have all of these different possible angles. Because there's so many different angles that have the same cosine value, if we don't make some kind of an adjustment to our definition, there's going to be infinitely many answers for every inverse trig function, right? Inverse cosine of -1/2, we could just keep going around the unit circle as much as we want, and we could keep listing more and more angles here. And so the restriction that we're going to do is we're basically going to limit what the angle can be to being between 0 and pi. So what I'm going to add here is that inverse cosine of x is equal to theta if cosine of theta is equal to x, and then additionally, theta is between 0 and pi. So theta is supposed to be between 0 and pi. And so in other words, we're basically limited to looking at angles that are in this part of the unit circle. And let me add it here as well. So it's asking you to find an angle theta. In interval notation, we could say that that angle theta has to be in the interval from 0 to pi. So anytime you're evaluating an inverse trig function, and that we'll see that something very similar is also true for inverse sine, you're not just looking for any old angle that works, you're specifically looking for an angle that is in a specific part of the unit circle. Because otherwise there would just be too many different possible answers. We want to make our function nice. We want to make this definition so that there's only one possible answer. And so if we look back at everything we came up with here, these ones don't actually work. So these are not in the right part of the unit circle. They're not in between 0 and pi, so they don't work. Okay, so let's get into some actual examples so we can see now how like a typical example of evaluating inverse cosine would work. Okay, so first example is inverse cosine of square root of 2 over 2. So what is this really asking us to do? Well, it's asking us to find an angle. And remember that because we're dealing with inverse cosine and because of the definition we just wrote down, that angle should be between 0 and pi. So we want to find an angle between 0 and pi such that cosine of that angle is square root of 2 over 2. So that means that we want the x-coordinate of our angle to be square root of 2 over 2. So let's try to find an angle that works. So if we were to go to an angle of pi over 4, that would be this angle here. Well, that's going to work, right? Because the x-coordinate of that point is square root of 2 over 2, and then the y-coordinate also happens to be square root of 2 over 2. And then why else does that work? Well, because that's in the right part of the unit circle, right? We always want to be looking for, and maybe I shouldn't say the right part of the unit circle. Specifically, it has to be between 0 and pi. So it's not even just the part of the unit circle. The number of the angle you're giving has to be between 0 and pi. So let me write this down. So inverse cosine of square root of 2 over 2, that is going to be equal to pi over 4. And actually, let me add a little bit of different color coding here to be kind of consistent with what we were saying before. So square root of 2 over 2. And so why is this the case? Well, this is because cosine of pi over 4 is equal to square root of 2 over 2. And then additionally, our angle, pi over 4, that we gave as an answer is in the correct part. It's in the correct kind of range of angles. So it's in the angles between 0 and pi. So just to give an example of something that would not be a correct answer, what's another angle that also has an x-coordinate of square root of 2 over 2? Well, negative pi over 4, right? That seems like that could also work. But it would not be true to say inverse cosine of square root of 2 over 2. That is not equal to negative pi over 4. And it is true that cosine of pi over 4, or sorry, of negative pi over 4, maybe I'll write this down, because even though cosine of negative pi over 4 is equal to negative root 2 over 2, that part, or sorry, positive root 2 over 2. That part is true. The issue is that negative pi over 4 is not in the interval from 0 to pi. Right? It's just not, it's less than 0. It's not in that same part. Just to give one more example, another angle that would not work is if you were to go all the way around and back like that. So that would be the angle, that would be 9 pi over 4, right? Because 8 pi over 4 would be 2 pi, 9 pi over 4 would be an extra pi over 4. So this would be the angle 9 pi over 4. So that one also seems tempting, but it is not true that inverse cosine of root 2 over 2, that is not equal to 9 pi over 4. And again, because even though it is true that cosine of 9 pi over 4 is equal to root 2 over 2, that part is true. 9 pi over 4 is not in the correct range of angles. It's not between 0 and pi, and so it just doesn't work. So yeah, so basically it's asking you to work backwards, but kind of with this extra restriction is the way that you can think about these. Okay, so next up we have inverse cosine of 0. So this is asking us to find an angle. Specifically, we want to find an angle that is between 0 and pi, right? So we're always looking for angles in here. And we want to find an angle such that cosine of that angle is 0. And so what does it mean for cosine of an angle to be 0? That means that the x-coordinate should be 0. So what is an angle between 0 and pi such that cosine of that angle is 0? Well, pi over 2. Right? If we go to an angle of pi over 2, the coordinates are 0 and 1. And so our answer is going to be pi over 2. And again, I'm just going to write this out in words. The reason that this is our answer is because cosine of pi over 2 is equal to 0. And then the other important part is that that angle, pi over 2, is in the correct range of angles that we're looking at. It's in the interval from 0 to pi. Okay, one more, and then we'll look at inverse sine, and we'll see that inverse sine is really similar. There's kind of one important difference. So inverse cosine of negative 3/2. So you might notice this is like a kind of a weird, you might think I made a typo. It does not say root 3 over 2, it just says negative 3/2. So this would be asking us to find an angle in this part of the unit circle such that cosine of that angle is -3/2. So this one actually does not have a solution. This one, you might say it equals DNE. So why is that? What would be the argument for why inverse cosine of -3/2 is undefined? Well, remember that what we're looking for here is we're trying to find an angle such that cosine of that angle is -3/2. So let's think about what -3/2 looks like as a number, right? It's less than -1, right? It's like -1.5. And so remember that cosine of an angle can never equal -1.5, right? The smallest it could ever equal is -1. So the reason that this is undefined is because there is no angle theta such that cosine of theta is equal to -3/2. And the reason for that, again, is because cosine of theta, no matter what the angle is, it's always going to be between -1 and 1. And so there's no way to get an output for cosine that is less than 1, which is what we have here. So this really comes down to the domain and range of inverse cosine, and that's something we'll get into a little bit more in the next video. Okay, so I want to now talk about inverse sine. So just like with inverse cosine, we have a definition, and we're going to have kind of a restriction for what part of the unit circle we're going to be looking at, and it's actually a little bit different for inverse sine. So the one thing that's going to be different here is really the part of the unit circle we're looking at. But yeah, so let me just write down some kind of general information here. So the inverse function of f of x is equal to sine of x is going to be f inverse of x is equal to inverse sine of x. So just like with the inverse cosine, we pronounce that out loud as inverse sine of x. And just like with cosine, I'm not going to write this all down again, but it doesn't mean to the -1 power, it just means inverse. And then just like with cosine, what I brought up, there is another name for it. So the other name for inverse sine would be arc sine. So arc sine of x, if you ever see that, that means the exact same thing as inverse sine. Okay, so what is the definition of inverse sine of x? Well, I'm going to write something down very similar to what we had before. So inverse sine of a number x is going to be equal to theta if sine of theta is equal to x. And then in this case, the part of the unit circle we're going to actually be looking at, it's no longer going to be from 0 to pi. It's going to be from -pi/2 to pi/2. So in some ways, that's going to make things a little trickier. We just have to be careful about the names that we give our angles, but basically we're going to be always looking between -pi/2 and pi/2. So inverse sine of x is equal to theta if sine of theta is equal to x, and additionally, theta is between -pi/2 and pi/2. And by the way, if you're curious, like why is it a different part of the unit circle, that's something we'll get into in our next video when we'll look at the graphs of these trig functions and their inverses and kind of see how it has to do with these functions being one-to-one and making a restriction so that they are one-to-one. And we'll see that the restrictions are different for sine and cosine, and that's really why we have to look at different parts of the unit circle. So let me just kind of write this down the same way I did for the other one. So in other words, if you're asked to evaluate inverse sine of some number, it's asking you to find an angle. We can call that angle theta, such that, let me add this in here. So it's an angle theta, and we want that angle theta to be in the interval from -pi/2 to pi/2. so between negative pi over 2 and pi over 2, such that sine of theta is equal to x. So again, asking you to work backwards and find an angle, this time between negative pi over 2 and pi over 2. So let's get right into a few examples with inverse sine. So first one is asking us to evaluate inverse sine of square root of 3 over 2. So that's asking us to basically find an angle, and specifically we're going to be looking for an angle that is between, sorry, I'm trying to change the color of this, find an angle between negative pi over 2 and pi over 2. So we're looking at this part of the unit circle. And we want to find an angle such that sine of that angle is square root of 3 over 2. And so that means that we want the y coordinate to be square root of 3 over 2, right? And so what would be an angle that has a y coordinate of square root of 3 over 2? Well, that would be pi over 3. So pi over 3, the x coordinate would be 1/2. The y coordinate, which is what we're interested in, would be square root of 3 over 2. And so inverse sine of square root of 3 over 2 is equal to pi over 3. And again, the reason for that is because sine of pi over 3 is equal to square root of 3 over 2. And additionally, our angle pi over 3, for inverse sine, it has to be in the interval from negative pi over 2 to pi over 2, right? It's between negative pi over 2 and pi over 2. It's not bigger than pi over 2 or smaller than negative pi over 2. Maybe just to give one example, again, kind of like we did with the other one, an example that maybe seems like it would work but doesn't. So for example, if you were to go to the angle 2 pi over 3, so 2 pi over 3, well, that also has a y coordinate of square root of 3 over 2, right? So that would be negative 1/2 square root of 3 over 2. And so, it might seem like that would be a good candidate, right? So it might seem like inverse sine of square root of 3 over 2 could be equal to 2 pi over 3. But that is not the case. And so why is that not the case? Well, because even though it is true that sine of 2 pi over 3 is equal to square root of 3 over 2, that part is true, 2 pi over 3 is not in the correct interval, right? It's not in between negative pi over 2 and pi over 2. It's too big. And so again, really the whole reason, these rules might seem kind of weird and strict, and like, why are we focused on only having this, answer between negative pi over 2 and pi over 2? It's so that there's a clear answer, right? If we didn't have that restriction, how would you know what inverse sine of square root of 3 over 2 would be? Like, there would just be too many different answers that it could be, and we want there to only be one answer. Okay, so let's do 2 more examples, and that will be it for this video. So next up we have inverse sine of negative square root of 2 over 2. So that's asking us to find an angle such that, and an angle specifically between negative pi over 2 and pi over 2, such that sine of that angle is equal to negative root 2 over 2. So what would be an angle that has sine equal to negative root 2 over 2? Well, we know it's going to be some kind of a multiple of 45, and then we also want it to be negative, and so that really makes us have to go down here. And so let me write the coordinates of this, and then there's something important to mention here, which is that I think it's very tempting to think, okay, well, I'm in the right part of the unit circle, I can just measure it this way. But that would actually be wrong. So if you have an answer that is in quadrant 4, you have to give it as a negative angle. And the reason for that is because our restriction is negative pi over 2 to pi over 2, right? It's not anything else. It's just between negative pi over 2 and pi over 2. And so we are actually forced to measure this angle as negative pi over 4. And I'll write that down because I think this is an example that I think it's really easy to think that it could be a different way. So inverse sine of negative root 2 over 2 is just equal to negative pi over 4. And the reason for that, again, is because, first of all, sine of negative pi over 4 is equal to negative root 2 over 2. So checks that box. And then the other thing we're looking for is that our angle, negative pi over 4, is in the interval from negative pi over 2 to pi over 2, right? Negative pi over 4 is in between negative pi over 2 and pi over 2. So just to kind of write down what I said earlier, you might think that, like, why can't I just measure it this way, right? It's the same angle, but it's not the same angle, right? Negative pi over 4 is not the same angle as measuring this way. That would be 7 pi over 4. They're coterminal angles, but they're not actually the same. So even though it kind of is tempting to say that inverse sine of negative root 2 over 2 looks like it could be equal to 7 pi over 4, that's just not true because, again, I know this is getting a little repetitive probably, but because even though it is true that sine of 7 pi over 4 is equal to negative root 2 over 2, and even though it looks like it's in the right part of the unit circle, it just is not true that 7 pi over 4, it's not in the interval from negative pi over 2 to pi over 2, right? It's not between negative pi over 2 and pi over 2. So that is not the answer. Okay, one last example. So inverse sine of 2. So this is asking us to find an angle between negative pi over 2 and pi over 2 such that sine of that angle is equal to 2. So this one is also no solution, right? Or does not exist. And so just like with the example that we did with cosine, the reason for this is because there basically is no angle theta that would work. There is no angle theta that would satisfy sine of theta is equal to 2, right? Because we just know that, like, the way that sine and cosine work, you're never going to get an answer out that is bigger than 1 or smaller than negative 1. And so this does not exist. All right, so in our next video, we'll do a little bit more practice. We'll also talk about inverse tangent and look at the graphs of the original trig functions as well as the inverse trig functions to hopefully give you a little bit more insight into why we have to look at these specific parts of the unit circle, these specific angles as our restrictions. So I'll see you all in the next video.